Okay, welcome everyone. So today we are going to continue a bit about what do we need from the compressor performance, what equations do we need, how do we calculate stuff when you have a dry gas compressor. So I'm going to show you some of the expressions based on what we saw yesterday. Maybe I will go a bit back into it, but I will show you some of the expressions that we can use to compute some important things, okay, that we need to calculate. And then we are going to do a class example that will be based on an exercise last year, I think, or 2 years ago. And then for the exercise, for the assignment, you will get something very similar, okay, but for Gulfax that has a network. Okay, so so yesterday we have seen that there is something called adiabatic efficiency. If we have a compression process, okay, then the most natural way will be to relate the actual compression, okay, the actual. I told you that the equation was W equal to mass flow times H2 minus H1. Is it? Yeah. And the most natural way to try to calculate this H is to say first, what is the smallest delta H that we need to compress from one P1 to certain P2? What is the smallest amount of, and this we call work, okay? This, the W over M, that we call a specific work, right? I think you remember that from thermodynamics. Specific work, okay? And it's just work or energy divided by mass, or if we have a steady state system where we have a continuous, entering and like in this case we have mass entering and leaving the domain, we can do also the same thing but with power and also mass flow. So we said, okay, the smallest energy that we can use from 1 to 2 to take from P1 to P2 is the isentropic path. That's the smallest that I can get. H2S minus H1. H2S not sulfur, okay, no, but enthalpy. That's the smallest power, okay, or specific work. Okay, required to compress from 1 to 2. And then we can relate, in reality we have actually that the entropy increases, because that's what happened in any real machine. And because of that we saw in the diagram that the temperature was also going to increase. So the smallest temperature, T2S, is the smallest temperature from 1 to 2, the smallest temperature. And that also, remember that some of the constraints that we listed last time was that the temperature has to be below certain value because the integrity of the pipelines, because the seals of the compressor, and because if we have MEG injection, to don't evaporate the MEG. Okay, the MEG has a very, well, not low, but it has 150 degrees Celsius, more or less, the vaporization point temperature. And if we go more than that, then it's not making it function, okay? We're just investing a lot of chemicals. Remember, these chemicals, they are almost like, gasoline, or it's very expensive. And yeah, more than that. And we don't want that it doesn't fulfill its function. It has to do its function, which is to be with the water phase, with the free water, and trying to inhibit the formation of hydrates, so we won't have problems in the pipeline. Okay, and we also define one efficiency that we call adiabatic. that we say that actually we have delta H isentropic divided by delta H real. Okay? The problem with this efficiency is a very nice concept, but the thing is that this adiabatic efficiency doesn't follow a trend. Okay, it's difficult to relate it with the performance of the machine. Okay? So another approach is to use a polytropic. Assume that the compression process, so this efficiency is difficult to relate it with the rate, okay, and it's difficult to relate it also with delta P. It doesn't follow a trend, like in the case, I think I showed you on the pump, if you remember. Let's see here just an example for the pump. Okay, if you remember the efficiency of the pump versus the rate, it does something like that, okay, because we design the blades are designed on a particular incidence angle, okay, and if we go more than that, then it's going to detach the fluid and it's going to begin to create these, turbulences, and if we go less than that, also it's going to do the same thing. So okay, so it's more or less the same principle, but this efficiency, the way it is defined here, it is difficult to relate it with rate and pressure. So people came up with the polytropic process like a best way to approximate, and this polytropic process, actually they managed to find a relationship with rate and pressure. Okay, so assume a polytropic process. I'm changing color here just to see if you're awake, to change a bit. Assume polytropic process, okay, and then I think we can take, okay, assume just a polytropic process. PV to the n is equal to a constant, and then the n you adjust it depending on what's the performance of your compressor. If you have a very poor performance, remember that you have 1 here and the pressure 2 is here, okay. So if you have a very nice process, here you have 2s, okay, the isentropic path. If we say that this is pressure versus enthalpy, so we saw that the isentropic was something like that, but then we might have any other kind of process that does like that, does like that, does like that, and then we can find, for each one of them, we can find a polytropic coefficient, okay? Okay, and then one thing that we need is the temperature at the outlet, and I told you that P2 over P1 to the power of n minus 1 over n is equal to T2 over T1. So if we have conditions at the inlet, and if we have also the conditions that we want at the outlet, and we have this polytropic coefficient that I will show you now, we want to have, is really not this coefficient, we want to have some kind of efficiency. Okay, all the time the machine, like the nice thing about this adiabatic isentropic is that it's a value between 0 and 1. Okay, so this n really can be anything, can be any number. So we really want a value that is bounded. Okay, that should be also between 0 and 1. And we are going to come very soon to something called polytropic efficiency. Okay, that is related with, is a function of this polytropic exponent. And then it's bounded, is between 0 and 100, and we can actually make good guesses, depending if it's a centrifugal or if it's a radial or axial compressor, where that value should be. Okay, so that's the idea. N is nice for the process, but we really want to have a polytropic efficiency, and there is a relationship between them. Okay, so let's see. If you assume a polytropic process, if a polytropic process okay, then this delta H can be expressed as T1, okay, C average, then R, which is the remember we have R universal and we have the R of the gas, okay, which is R universal divided by the molecular weight of the gas. Okay, then we have N, the polytropic coefficient, N minus 1. Then we have Rp, which is Rp is the pressure ratio and is P2 over P1 to the power of N minus 1 over N minus 1. Okay, and that's simple. It's a simple expression. Okay, we just need this factor that really this is the average Z1 plus Z2 divided by 2. Okay, but we are going to make the approximation like we have done in this course, that is the Z at the inlet. Okay, the temperature at the inlet, these are that we know how to calculate it, and the polytropic coefficient. If you see here, what is that I'm presenting here? If you see, you try to relate this equation with this equation. Is T2 minus T1, right? Divided by T1. Yeah? That makes sense? Yeah? So, you remember enthalpy, I'm not sure if you remember, but from your thermodynamics, did you see it? No? Yeah? If you take here, this is Rp, N minus 1 over N, T2 over T1, okay? And then you pass multiplying T1 here. Okay? And then we pass everything, this part to this place, right? Yeah, I'm missing something here. Oh no, yep, you have to put T2 as a function of T1, and then, yeah, just made a mistake here. Okay, T2 is a function of T1, so when you substitute here you have T1 Rp N minus 1 over N minus T1, okay, and that's T2 minus T1, right? Yeah. And then T1 can come out like a common factor, and then you just have, did you see it now? Yeah, okay. When sometimes I go a bit quick, just let me know and I just stop, and even for me it's good the clarification. Now suddenly I got into trouble, but that's okay. Okay, so this delta T, and if you remember from thermodynamics course, usually you can assume that delta H for liquids especially was kind of a constant times a Cp times delta T, right? That's an approximation that you were using for liquids. I'm not sure if you remember for liquids. Okay, in this case it's a gas, so it's slightly different. You have all of these parameters, but still follows the same trend that the enthalpy difference is related with the difference in temperature. Okay, so this resembles, let's put here, because I don't want you to have wrong notes, but resembles a bit, okay, the expression for liquids, okay, the approximation that we can make for liquids. So that's delta H, and this we call it polytropic because this is calculated assuming a polytropic process. Okay, now we can define also, now if we have this delta H polytropic, we can define exactly a polytropic efficiency that is going to be delta H isentropic divided by delta H polytropic. It's exactly the same expression that I had before, okay, but now I'm going to use this expression for the part down here, okay, for the delta H down here. And what am I going to use here? I should have also something a bit similar, okay? So we can do the same thing for isentropic, if I can find it. Here. Okay, and K is the relationship between the specific heats, that is Cp over Cv, I think. Yep. Okay, we have here people that remembers their thermodynamics. Okay, and you can reach the same expression if you assume isentropic. You can reach also to this analytical expression. So that tells you that the polytropic, that gives you, if you divide these two and you do some manipulation, that gives you this expression. Okay, that is relating this exponent, the polytropic exponent. Don't be confused. This is the polytropic exponent. This is, how do we call K? Adiabatic coefficient. And then we have the polytropic, the value that we wanted, okay? Have an efficiency, something that is between 0 and 1. Polytropic. So if you see, it's very similar to the isentropic, to the adiabatic efficiency, but now we found a way to still use Rn and still use an efficiency that this efficiency is going to have a trend. It's going to have a performance similar to what we observed in the pump. Okay, so that's the usefulness of having this expression. Yep. Okay. And this K, we can also calculate it. This is a formula that is typically used in compressor design, and it's an approximation, but it actually works quite okay. So here, okay. For hydrocarbon gases, this K has the following expression: 1.3 minus 0.31, specific gravity of the gas minus 0.55. Okay, trying to relate it, the deviation with respect to methane. Adiabatic coefficients also is called adiabatic exponent. So, no problem. If we have the specific gravity of the gas, we can calculate this K, and if we have N, or if we have the efficiency, we can calculate the N. It's exactly equivalent. So far, so good? Yeah? Okay, now let's see how we can use this. Before we go into the exercise, so this efficiency, we can say that for radial compressors, okay, typically the value goes between so many pages. Goes between 0.6 and maybe 0.77, okay, for radial compressors, and for axial compressors then it can be greater. Usually it's between 0.8 and 0.85 more or less. Okay? And the reason of that is, remember, in radial I'm doing acceleration and diffusion at the same time. So I have a big chance that I have all of these recirculations. When it's axial, I have less chance that I will face these issues. Okay, so we have almost everything. We have the way to calculate. How do we calculate power? if we have this expression, if I give you, for example, we are going to use now for our exercise, we are going to use for class exercise that the polytropic efficiency is equal to 0.73. Okay? And we know that's going to change with the rate, but we are going to keep it fixed. Okay, more or less 7. That means that it's quite flat. We are assuming that even though we know it has this behavior, this is the actual rate, and this is the polytropic efficiency, we are assuming that we are working, trying to operate the compressor in the flat area, okay, in the more or less constant area. That's an assumption that we are going to make. Okay, so how do we calculate power? Remember power, so we have how to calculate temperature. That was one of the things. Then we have how do you calculate power? Yeah, the work times the mass flow, okay? Delta H polytropic times the mass flow, okay? So that sounds okay. We have an expression for that, and the mass flow we can calculate however we want, okay? We can use the standard conditions rate times the density at standard conditions. We can use the actual conditions rate times the density at actual conditions. We can have many ways how to calculate the mass flow. And what else do we need? Temperature, power. What else did we mention last class? Okay, we said P suction, that really we don't need anything to calculate. That's going to come from the hydraulic equilibrium. Minimum and maximum flow, that we need a compressor map. Okay, that we need something that defines these two lines on the edge. So we're going to have now a bit small discussion about that. Frequency also we need a map. Require power and T outlet. So I think we are more or less done, more or less. So the only thing is to talk a bit about performance curves of the compressor. Okay. Before we go there, there is that is delta HP. There is also another variable called polytropic head. That is nothing more is depicted by the letter H, P, and is nothing more than delta H P divided by the gravitational acceleration. Okay? And the idea is to use a kind of, if you remember in pumps, we divided delta P over density, and that gives you also head, that is in meters. So the logic is more or less the same. We want to get something in meters, okay, to get some kind of a head, but it doesn't matter much. The thing is that some people, to plot the performance of the compressor, they use this polytropic head. Okay, so what kind of maps do we have? If we plot, like following the same case as the pump, we plot Q, and this is actual rate. Okay, it's the Q local. Okay, we call it actual, or in our course we are also calling it local rate. Okay, versus one way to plot it is they don't use delta P, okay, but they use RP, P outlet divided by P inlet, okay, and how it's going to look like that, okay. Remember, not many mysteries, like that, or but nothing like this, okay. That's nature. That's okay. So it looks something like this. And this is for every, in this case we don't talk about frequency, because in this case we talk about RPM, okay? And we, instead of using letter F, we use N. Okay? So that's how it looks like, very similar to a pump. And here we have these lines, or we can also have another type of chart. We can have just the pressure at the outlet versus Q local, and it's going to have exactly the same trend. Or we can have, and that's the most common way, we can have HP, this polytropic head, that is giving you this, this difference in enthalpy, this specific work. and it's going to again to follow the same trend. Okay, different numbers but exactly the same trend. Okay, the thing is, something that is very different to pumps is that each one of these plots is a function. It depends on the conditions of pressure at the inlet, temperature at the inlet, molecular weight of the gas, and K. It's a function, okay? The same machine, exactly the same machine, if now I change the inlet conditions, it might look something like this. Okay? These are with, let's say, P1, sorry. These curves in black, they are for P1, and these curves in red are for P1 star. And why is that? Anybody has an answer?
Change in density.
Yeah, the change in density, okay? Remember that the velocity, basically the performance comes given by the velocity that we have on the if we have the blade, okay, we have the velocity that is inciding on the blade, okay? If we have the same volumetric rate but we change the density, then we are changing the velocity. So we are changing the performance of the machine. Okay, so it's just to put it simple, is because of that, because you're changing the density and the properties of the fluid at the inlet or inciding to each blade stage. Okay, so that creates kind of a problem because we have to find a way to predict. If we have these curves, probably we have them for certain conditions. Okay, and we have to find a way to predict how are they going to look like for some other conditions, okay? Because probably we won't be operating exactly with these conditions. We will have a different gas. The pressure at the inlet is going to change with time, okay, like we have seen. Then the temperature might also change because you get more cooling, etc. Okay, so how do we deal with that? So let's put that small comment here. Usually, I also want another comment. The same thing happens when you have multi-phase flow. When you have a bit of liquid in the gas, okay, that's also changing the density and the properties of the fluid. So you also have a change in multi-phase flow because of GVF. Okay, the GVF changes and then the curve is also going to change. Let's take it out. Okay. Usually compressor performance curves are measured P1 and T1, okay, they are controlled. The manufacturer, they come and they measure their compressor, how it behaves, and they have P and T1 that are usually standard conditions, okay? They try to say at 1.01325 and bar and temperature 15.6. Okay. Sometimes they are a bit different, but and they use a particular fluid. Okay, typically they're also tested with air, okay, that has certain molecular weight and has certain K. Okay, then we say how do we if we have those curves, okay, let's talk now about polytropic, that is the enthalpy difference, Q actual. If we have these curves measured for P1, T1, molecular weight 1 and K1, okay, how I'm going to convert, or how am I going to find the actual performance for my particular case, okay, because now I have P1 star, T1 star, MG1 star, and K1 star, okay, that they might be different from the test. Okay. Well, we are not going to go into details into that, but actually there is a procedure how to using similarity loss, there is a procedure to say to try to find what will be the equivalent curve for different inlet conditions, different operating conditions. Okay, we use thermodynamic calculations and transformations to convert from the test, what was measured in the test, to what I'm actually going to have. And maybe I can paste right away the expressions, okay, so you just have them. You don't have to know them, but you have to know more or less. It is based on similarity, okay? It's based on making that some parameters are constant in this case and in this case. So let me see if I have them here. Okay, so these are correction. They are called correction factors, and you have the correction for the flow rate, and we have a correction for the polytropic head. Okay, you can create correction for any other factor that you want, for RP, for okay. Now the main problem is that if you think about it, then for every year, okay, we are going to do our analysis in every year. We are going to have a different compression map. That's going to be a bit messy. Okay, from the design point of view, the beauty of, if you remember what we had on the pump, okay, the pump, the beauty that it had is that we were able to plot all points in the same plot, okay, and then we were able to see if it falls inside or not. If in this compressor, looking at that, then we will have one map for year 1, and then we will have another map for year 2, then we will have another map for year 3, which really it's just going to take space, and it's not so nice, okay, it doesn't look so nice. So what we are going to do, and what is typically also done, is that we are going to use, instead of converting the performance curves to the real performance, we are going to convert our real point to the test, okay, just using the inverse of the correction factor. Okay, then if we put everything in the same reference, all the points are going to be in the same map. I can plot all the points in the same map. Okay, so that's what we are going to use, and that's what's programmed. But just don't pay too much attention. But just you have to understand, you know what, we are actually going for the exercise. We are actually going on that direction only for the exercise. Let's put a star here and put it here to avoid generating performance map for every year. Okay, and I show you how to, so you have to use basically these correction factors, but the inverse of them, because the correction factors, you use them to go from what you measured in the lab to what you actually have, and now we want to change for what we actually have to the map, and we want to change only one point, okay, because in this case, remember that the curves, they are formed by a collection of points, okay. So we have to make the conversion on each one of the points. We have to apply this correction factor to each one of the points. And that becomes, I have to convert it for every time. So let's say this point will map to, let's see, how do I do it without spoiling the figure? Okay, this point is going to become this point after I apply the correction factor. This point is going to become this point after I apply the correction factor. Instead of changing all points, I'm going to take just my operational point that is going to be here, okay, operational point, and I'm going to put it back here. So I'm just correcting for one point. I don't have to correct the whole curve. Yeah. By the way, did you see that already in one of the courses here at the university? No? You didn't took any course in compression fundamentals? No? In processing, you don't see that? No? Okay. So let's say, did I put that already? To avoid generating performance map for every year. Okay. Okay. And I think then we are good to go to the exercise. Oh yeah, just one thing that was missing, how the map looks like. Okay, I told you that there are limits. So the map actually, that was a very straight line. Q local. Okay, and it looks like that. And actually there is here one area that I told you this is called, it's called stone wall, or is where you have also choked flow. Okay, and in this case the velocity of the fluid is equal to the velocity of the sonic velocity. I think it's called with the letter A, sonic velocity. Okay, the fluid goes as quick as the velocity of the pressure perturbations in the gas. Okay, so in that case I will have problems because I cannot increase the rate any longer. So that's this limit here. Then you have another limit here that is called surge. Okay, and that's because again the rate is too low, and what happens is that it enters in some kind of a transient. Okay, the rate goes inside and outside of the compressor. It goes both ways, backwards and forwards, because it's too low, so it creates some instability that it creates flow, reverse and forward flow. Okay, so we want to be away of that line. And also this point, like in the pump, if you remember here we had a frequency of 60 Hertz, that was the maximum frequency that was given by the maximum power of the machine, the maximum, the motor power capacity of the motor. And just curiosity, we are not going to go too much in detail, but usually the efficiency lines do something like that. Okay, these are ISO efficiency lines. So here you will have an efficiency, the best efficiency, efficiency 1. Then you have the second best efficiency, efficiency 2. The third best efficiency, efficiency 3. Okay? Just curiosity. It looks like a topographic diagram. There are lines that have the same efficiency. Okay, so now let's go, and before we take a break, let's see a bit what exercise do we have for today. So it's not here, here. Okay, it's the same Snøhvit system. We have 9 wells. Okay, they split it into 3 templates, which makes it easy. We need to have only 1 well to compute. Okay, we have already computed the end of the plateau, and now at the end of the plateau they say we are going to install a compressor station after the PLEM. Okay, actually if you see the plan from Statoil, that's actually what they are going to do. Okay, the production strategy, they didn't put all wells like in our case in production at the same time, but they were including first 2 fields. Okay, then they have the decline. Well, actually this is plateau. Okay, this is plotting the potential, what we were using. I'm not sure if you remember potential, that was already centuries ago. Huh? You remember potential or no? So this is how much the field can produce, and this is what we are actually producing. Okay, when the potential gets equal to the rate, then we are going to have the end of the plateau. But here we have that another field or another formation is coming into production, and then we have some more years, but at the end we don't have anything else. So what we have to do is installation of offshore compression. Okay, so let's copy that. And by the way, boosting is going to become more and more, because before it was a technology that people had a lot of resistance. Okay, there were not many cases that were using it, not many experience. The manufacturer also could not guarantee certain performance. But now, after some years of testing and some pilots, it's becoming more and more accepted by the industry. So my impression is that in the future you will see more and more installations with either subsea boosting or subsea compression, and so it's an advantage that at least to solve the exercise. Okay, so that's our system. That's the plan. Let's see. So let's see class. Okay, that's for the Snøhvit field. Snøhvit. And we are following more or less, we don't have exactly the same data. We have a very simplified model, but we are following more or less, I think here I just can, that we want at the end of the plateau, so there won't be any decline, to install offshore compression. And at the plan, because we don't want to put a compressor for every group of wells. Okay, we want to put just one compressor, one installation. That will be cheaper than put many compressors, small compressors in all the lines. Okay, we have only one place, and we have okay, and then you have change of the separator pressure, onshore compression, and then you have final decline of the field. Okay, actually quite a long plateau. If you see, it has plateau up to 25 years, I think, more or less. And I think the plateau that we got in class was like 20 years. That's where we are going to install the compressor. You see also that the potential is increasing when we add new fields, when we add new wells, and also when we add a compressor. Okay, we can produce more than what we do if we do it naturally. Let's see. Okay, and that's a yearly gas production, just more or less the same figure, but now with the, this is not secret. Okay, this is just, we have some presentations the last years and they are giving this information. So yeah, and so we are going to analyze the option that we have to install the compressor. We have actually 3 wells. We are just about to have a break, just be patient. It's not only you, okay? My brain also gets a bit tired after 1 hour teaching. Okay, so this compressor station, the way it's going to be done, it's going to have a cooler. Okay, the first part is going to have a cooler. Okay, we're going to assume really there is going to be, like in the case of Osgard, actually this is a dry gas compressor, so there will be a scrubber and a separation. But we are going to assume for our exercise that it's dry gas, what's coming from the field. Okay, but in reality you need to have a scrubber. Maybe we're going to put it here just for reference. So that's a scrubber where you have separate all the liquid that goes separately to a pump. Okay, and here you have the compressor, and the compressor, the way it's going to be done is there will be 2 compressors, parallel compressors, and they are mixed, and then at the end you mix and that goes out. Okay, And the cooler is just natural convection, and that means that it's working just with the water at the seabed. Temperature, and that's about 6 degrees Celsius. And we are going to assume dry gas in this exercise, so we are going to neglect dry gas in the exercise. Okay, so we are going to be neglected. Okay. But remember, in the general case, you need to have that because you're not sure. Probably you have condensation, you have liquids, and you have to separate. And also, you need to have injection of inhibitor, okay, of hydrates, and that's usually done in the wells. It's close to the wells, the injection. So that's gas with condensate, with free water, and with inhibitor. That makes sense or not? I think it's, terrible. I don't know how you have to say no. That looks like a free water inhibitor. Okay, so those are all the fluids that come inside. So you have to separate, compress, and then you have to join them. And there are many other things. And also there is a spare. There is another compressor typically, because we cannot, if we need the two compressors to have exactly the rate, the plateau rate. Okay, if something happens in one of them, maintenance, I have the electrical problem, we have erosion, etc. So we want to just close the valve. Remember, here I'm skipping all the valves, but these actually have isolation valves. Okay, so this is a spare compressor. And what I'm going to do is to put it in operation. This is normally closed, okay, and these two are open. If I have problems with one of them, I just close that valve and I open this one, and no problem. I can maintain production like if nothing happened. Then I go, I make maintenance, I pull out. Actually, these are retrievable, okay, so they are made so I can go and take the compressor out, take it to ground, take it to shore, and see what's happening with the compressor. Okay, no repairs. Usually I cannot do repairs on the seafloor. Okay, so we want to analyze. We already have a compressor, but let's first do what we did for the pump, a simplified analysis, just taking the minimum amount of constraints that I have to honor, and then I go and check on the map if the compressor that they propose is good for my case or not, right? Okay, and also, before we take the break, remember that we are now, you see, it's very complex, okay? It has a lot of pipes and lines and everything, but with the equilibrium analysis, we're going to make the required pressure here and the available pressure here. And we are going to neglect, in a way, all the complexity that is happening inside. But basically, what is increasing the pressure, here you have some pressure loss in the cooler, not much, we are going to neglect it. On the scrubber also you have some pressure loss, also we are going to neglect it. Passing through all the conduits also we have. So the main pressure drop is going to come from the compressor. Okay. Yep. So let's take a break, 15 minutes, and then we continue with the exercise. I'm going to upload an Excel file, so if you want to do it also at the same time, you can download it from Miss Learning. Okay. I got some interesting questions on the break. One of them was that why do we need to separate, okay, here at the beginning? And the reason is because these compressors, these are centrifugal compressors, okay, or they are radial compressors. They don't tolerate very well liquids, okay. The liquids, they can do a mess inside the machine. they can cause erosion, they can cause all kind of problems. So we prefer to operate them in single phase flow. That's why we have the scrubber. And then the fluid, this liquid is going to be at a lower pressure. So that's why we have to put all of them at the same level. The two streams at the same level. And this approach is used also because you will see that the delta P is quite high. Okay, the delta P needed is high. Okay. Another option is to use a wet gas compressor. Okay, that you don't have to separate. You just put everything this compressor tolerates. If you remember, how was the remember that it had some. By the way, you know what that represents, right, or not? These small things, like that, the blade, yeah. Okay, but this is kind of 3D that you have. This is the hub, okay, and this is rotating, okay. But if this visualization, if you cut it, maybe it's a bit late for this question, but okay. If you cut it here, you make a plane like that, and then you unfold it, and then you see the rotors in from the top. Okay, that's the visualization. Okay, and so in this case, remember that the pressure increase per stage is very small. So I will need a lot of stages. So usually these type of compressors, they are limited to a delta P less or equal than maybe 40 bar. Okay. If I need something else, I will have to be either put a lot of compressor one next to the other, or I have to, the compressors in series. Okay. So that's why I prefer to separate and then to use just centrifugal compressor that is working with just with dry or with one single phase fluid. So before, here I open the Excel sheet, and we will go a bit just now, what it has inside. But I wanted to write very kind of clear what are the requirements. So the polytropic efficiency of the compressor, assumptions for the exercise, assumptions and also requirements for the exercise. Okay. The polytropic efficiency is usually changing, okay, but we are going to assume that it's constant, and we are going to assume a value of 0.7. Okay. Then we are going to say that the temperature at the discharge is going to be has to be less or equal to 150 degrees Celsius. Okay, that's because of seals integrity. That's because of the avoid vaporization of inhibitor, and to avoid structural problems in the discharge pipeline. Okay, all of that. So for that reason, maybe we will need the cooler. Okay, maybe if we all the time the temperature at the inlet is going to be I think it's 67 degrees Celsius at the inlet of the compressor, or at the inlet at the compressor station. Okay. And if we see for some reason that the temperature out with this polytropic efficiency is going to be greater than 150, then we have to do cooling. Okay. The cooler is operating with a temperature, ambient temperature of 6 degrees C, but it's using natural convection, so the H is very small, so you need a lot of area. So the maximum delta T that it can cause is more or less 20, I think 23. see. I forgot the actual number, but I think it's close to 20 something. Okay, let's say that it's 27 degrees Celsius. It doesn't matter, what is the flow. That's the maximum delta T that I can have in the cooler. Okay. Actually, the cooler itself is quite an interesting problem because it's a multi-phase flow that is coming into the cooler, and it has also a lot of channels, okay, mini passages. That is actually, maybe I have a picture or not. No. Okay. Well, I can find it in the break. Okay, what else do we need? Okay, now we need also the power of the compressor. Of each compressor unit. Is going to be, I think what we have in Gullfax in Osgard is 11 megawatts. Okay. So you have in total, you have maximum total is 22 megawatts. Okay. What else? Yeah, we can start with this. Maybe we will need something else, but we can start with this. You see, it's already a lot of constraints, and we still haven't gotten into the... So these are all operational constraints and compressor constraints. Operational constraints. And also general compressor constraints. Okay. But also we are going to have later, we're going to have specific compressor constraints. Okay, with the performance curve. And I feel like something is missing, but let's just start. Oh, the suction pressure. Okay, the suction pressure, it has to be greater or equal than 20 bar. Okay? Just because the manufacturers say to operate, for the compressor to operate with no problems, you have to have a minimum pressure of 20 bar due to sealing, due to many different issues. Yep. So we can start. We go to Excel, and here on the first sheet we have that you're already familiar. You're maybe a bit fed up with it. That is the Snøhvit example, and we have done already the calculation all the way to the end of the plateau. That is in year roughly 21, 20.76, and then from this point we want to evaluate, if what will be the compressor, how a compressor is going to operate. And here we have this plot, which is pressure evolution, and we also want to see how, if you see here, the delta P of the choke is this difference, and it's going to be reduced with time. Here we have fully open choke, and then here we will have compressor also. Then something that is important is the compressor, the pressure at the inlet of the compressor, and the pressure ratio, RP, and you will see a very interesting trend there when we do the calculations. Layout, equations, nothing else. This is the data. These are the conditions under which this data was measured. Okay, specific gravity 1, so that's air, P in 50 bar and 25 degrees Celsius. And these are the curves for different RPMs. And here, if you see at the end, we have the map. Okay, we have the map. Exactly, you know already what polytropic head means, on the x-axis is the local rate at the inlet of the compressor. And you have that actually doesn't have the RPM, but it has in percentage of the design speed. Okay, it can run up to 110 and 70%. And these edges, they are already defining, it already contains the surge and the stone wall limits. Okay. So first, what do we do to make the calculations? We have to calculate available and required, okay? But where are we going to place, where have we done up to this point the equilibrium? Do you remember? We were doing it in the choke, okay? So we were doing our calculations from the reservoir all the way to the wellhead. That's the available pressure. And then we did required pressure from the separator, pipeline, flow line, and then template, okay? But now this point, it's not going to be different because the choke is fully open. The two pressures are going to be the same. So we're going to move the point to the plem. That's where we're going to put our next equipment, which is the compressor. Just like we have done in I think we had an exercise like that in class, I think. Yeah. It was a very simple network with two wells that had a compressor. No? Okay. Well, so we have to move the equilibrium, okay? So let's see, this year will be year, yeah, we can put year 21. Okay. The rate, we want to keep the plateau rate because we have this contract with then the cumulative production also is going to be calculated the same way. The deviation factor, this is actually using what? Okay, Q per well. Okay, so first we calculate flowing bottom hole pressure with that rate and reservoir pressure and the IPR. That's okay. Then we calculate PWH, and this won't be available anymore, but that will be just a unique wellhead pressure. Then we calculate, after that we calculate, we have to continue, okay? We have, what do we have? Okay, we are moving from the well at the bottom all the way to the wellhead. But now this is not the equilibrium. We cannot stop there, but we have to continue from the template to the plem, okay? From the template all the way to the plem. Okay, so these two pressures actually they're going to be the same. Okay, P wellhead and P template, right? Because now I don't have any choke. Now P plem in this case is going to change from plem required to plem available. So this is going to call P template is equal to, well, actually we have to put numbers here, so yeah, let's see. Okay, now P plem is going to be equal to, this is line, which equation is it? Line P2, right? The outlet pressure of the pipe.
Outlet pressure of the pipe. P2 is
Yeah.
separated.
No, but if we are now looking at, we are now at the wellhead, okay, at the template, and we want to calculate the pressure available at the plem. So it's P2, right? Line P2. Okay, because we have the conditions in 1 and we want to calculate the conditions in 2. So line P2, and here we have C of the flow line. So here we have to have the flow line constant. We have to block it. Then we have the pressure at the inlet, which is this pressure. We don't want to block that. And then we have the rate, which is actually the rate of the template, which is here, okay? So I'm going to, even if it's empty, I'm going to drag it down, okay? So not much change from previous year. P plem available, and then I have to calculate P plem required, right? So let's put here one more column that is going to be P plem. Why is transparent? Okay, P plem required in bar. Let's do it the same way. Okay, and here we're going to go from the separator all the way to the plem, counter current. So that's line P1, okay? P1, and here I need, let's see, what do I need? The C of the flow line, that I have it someplace here, F4, then P2, that's the separator pressure, that is going to be 30. In this case it's empty, but I'm going to fill it very soon. And the rate, which is the rate of the field. Okay. And they should be in black. Okay. So you see they are different. The required is greater than the available. Okay, this up to this point is available. So let's put here available. Okay, the required. No, actually I have more, right? So what's happening here? Hmm?
You have to put separator pressure, 30 bar.
Oh, okay. Yeah, something was wrong. No choke. The choke is fully open. Okay. Okay, so let's see, what do we need for to calculate? We need first pressure at the inlet of the compressor, right? This is P plem available, right? Then we need the temperature. Okay, so let's put here temperature at the suction, and this temperature is going to be in Celsius. I don't know what happened here. And the temperature at the suction first we're going to approximate is just 67, okay? No change. Okay? No change, no cooling has been made. That's assuming that there is no cooling. Then one thing that was useful for was the compression ratio, RP, okay? And RP doesn't have any units actually. And RP is going to be equal to the pressure at the suction, which is this pressure, divided by the pressure at the discharge, which is this one, okay? And it's going to give you a value almost very close to.
It's less than 1.
No, actually should be the opposite, okay? The P2 divided by P1. Okay? 1.03. So I don't have to do too much boosting there. And now I will put also delta P of the compressor in bar. And that's going to be this pressure minus the discharge pressure divided by the suction pressure, which is this one, and 1.9 bar. Okay, not much. Then I have to put someplace what is the polytropic coefficient, okay, or the polytropic efficiency. The polytropic efficiency we said we are going to assume to be
0.7.
constant, 0.7. 0.7. If you have some values, then you can change it every year, okay? But now we are just going to assume that it's constant. What else do we need? So now we can calculate. Can we calculate the temperature at the discharge? Yep. What do we need to calculate the temperature at the discharge? We say that we had Rp to n minus 1 over n equal to T2 over T1. That means that T2 is equal to T1, just to verify if we need cooling or not. Okay, if the temperature will be greater than 150. RP n minus 1 over n. So we have T1, but we need n. Okay, how do we calculate n? I already gave an expression. Okay, I think I have programmed already that for you here. Let's see. Okay. Well, actually, this is the opposite. Here you have the polytropic exponent. Yeah, so this is exactly what we want. The polytropic exponent based on the efficiency and on k. Do we have k?
No.
No? We have to calculate k. So k, what was the expression? So
CP over CV.
yeah, but we had one expression with molecular weight, which is a bit better to use, right? 1.3 minus 1 point, huh?
0.31.
0.31 times I open here and the specific gravity. Okay, molecular weight or specific gravity here divided by
minus 0.5.
minus 0.5
0.55.
minus here.
Oh, sorry, instead of division, you're dividing specific gravity with.
Yeah, I think so. But that doesn't
just
look.
remove division, son.
Yeah,
And
minus here. Okay, yeah, that looks more. Okay, so I have k, and with k now I can calculate. Well, that should be actually blue because that's calculated. With k, I can calculate the polytropic exponent, and this is exponent. And here I need the k, which I already calculated, and I block it. And then the efficiency, which is here, and I also block it, and enter. Okay, so the exponent, you see that it's a bit similar. It's in the same order of magnitude of the isentropic, but it's different. Okay, so that's also something that helps us to do some quality control. These are data that we gave, and this is also data that we gave, and this is, what else did we give? Nothing else? Okay, so that's n, and n doesn't have any units. Okay, next step, temperature. Okay, let's calculate the temperature at the discharge. Okay, the temperature at the discharge has to be in Celsius. Okay, but in the equation it has to be in Kelvin. Okay, in this equation it has to be in Kelvin. All the time when we use thermodynamic expressions, the temperature, no matter what, I just tell you to avoid any mistakes, it has to be in absolute units. T has to be in absolute units. Okay, that means either in Kelvin or in Rankine, but it cannot be in Celsius or in Fahrenheit. Okay, so here we have first Rp to the power of n minus 1 over n and this times the temperature, right? So this times the temperature, you have to be sure that I'm not making any mistake, times the temperature here, plus 273.15. It has to be like that in parentheses, and then this is the temperature that I obtain, and I subtract, sorry that I didn't program that for you, 273.15. Okay, 69. We didn't make any mistake. Somebody's there verifying my calculations? No? Okay. Temperature at the discharge, it looks like there is no issue with that. Okay, so now let's calculate what else did we have? The power, okay. Let's, for the compressor map, we don't need it right away, but for the compressor map, we are going to need the local rate. So let's calculate, just to avoid having later to add a column. Let's just calculate it now. How do we calculate the local rate? If it's a dry gas, with BG, okay? You remember BG at certain pressure and temperature is equal to the Q of gas local divided by the Q of gas at standard conditions. So if you have the rate at standard conditions, then you can calculate QG local just like QG times BG PNT, which is just the same as to apply the equal masses in the equation of state, okay, in one condition and in another condition. And I think I have programmed for you that BG already. So let's look, let's calculate here BG, and that's BG at the inlet, okay, because that's what we are plotting. It's the local rate at the suction, at inlet, or the suction. And BG has units of cubic meter per standard cubic meter, right? And BG is equal to, it depends on the temperature, and that also has to be in absolute. So the temperature at the suction is this one, okay, plus 273.15. Then the pressure is this pressure here, right? That's the suction pressure of the compressor, and set, I need set, right? I didn't calculate it any place, the deviation factor.
I guess we have calculated.
Yeah, but that's for the reservoir. Now remember that we are at different temperature and pressure, okay? So let's just drag this here, and we are going to put set just next to it, okay?
So the pressure is now
Huh? What? Sorry?
in the equation, the pressure should be in bar or in pascal.
Yeah, I will check that just now for you. Just let me just fix that with set. So set deviation factor at the suction is no units, and here I use C fact standing, and the pressure at the suction, which is this one, the temperature at the suction, which is this one, the specific gravity, which is here, and I blocked this one, and the units, you remember which one was field and which one was metric? 2 metric? Sure? Okay, it gives reasonable result, okay? Let's just check just in case. So the C factor is, if unit equal 2, then it's metric, and the pressure is in bar, and the temperature is in Celsius, so that looks consistent. Now you go, I think at the bottom I have BG, temperature is in C, and P is in bar. Okay, that's what we are using. And actually now this should have already temperature, pressure, and set at the inlet. Okay, and then with this one we can calculate QG local.
The temperature is
Celsius.
The temperature?
Yeah.
No, the temperature should be in, if I made here is a mistake. Oh, yeah, because it has plus already. Okay. You are right. Okay, and then I calculate QG local, and that QG local is in a standard cubic meter, no, sorry, cubic meter per day, and it's just QG times BG. You are awake, that's good. If you're not awake, I don't know what, there will be a lot of mistakes. Okay, so that's the rate, the local rate, and we just have it in case because we will need it for the compressor map. What else do we need? I think we can just go and calculate the polytropic head, okay, the polytropic enthalpy, right? So we can say I want to calculate delta H P polytropic, and this delta, let's put it in okay, not that delta, but this delta is a bit rebel. Symbol. And this, which units did it have? I think it's kilojoule.
Kilojoules per kilogram.
Yep, I think so. And this, I think we have an expression in, I programmed for you already an expression, and it's okay, polytropic head. We have the head, but we remember if we multiply times the gravitational acceleration, we get the delta H. Okay, so no problem, we can use the same expression. It needs pressure ratio, it needs temperature at the inlet, okay? It needs set, that this was supposed to be average, but we are going to use just from the inlet. N, we have already calculated, and R, which is the universal divided by the molecular weight of the substance. Okay. So let's see if that makes sense. What was the name? HP. HP, and this has the pressure ratio that is here, that has the temperature that is here, and has to be again, I think in yeah, but here what did we have? Okay, in Kelvin. Okay, so we have to put 273.15. Then set, it's here. Then N is the polytropic exponent, is this one, and R is, what is the universal? 8.314 divided by the molecular weight. Okay, it gives 400. I'm not sure if we have done something. Huh?
That should be average or
The set, yes, it should be average, but this is an approximation for this class. Zeta average is more or less equal to the set at the inlet. Okay, set 1. But that's just for this class, because if you want to solve it, really you have to kind of assume a set, calculate the outlet conditions, and then you have to, well, no, we can calculate it, right?
We have T2, we can calculate.
Yeah, so let's calculate that. Just see discharge. Okay, and here we can copy exactly the same equation, but here it has to use the, oh, I forgot, this was temperature at the discharge. Okay, and the pressure, you should use the pressure also at the discharge. Okay, like that. So actually didn't change almost anything. Yep, okay, seems to be okay. And here I can use, like you said, just the average of these two is here, right? So I have to put plus this divided by 2. Yep. And it didn't change. Okay. Okay, now we have that, and we want to calculate the power. The power is just the mass flow multiplied by that, right? So how do we calculate the mass flow? Okay, so we can use the standard conditions rate, right, times here times the density of the air at standard conditions, right? What is that? 1.22. Yeah, you have good memory. 1 point. Okay, but these are not the units. Okay, this is in if you're multiplying Q at standard conditions, that's times density at standard conditions. That's in cubic meter per day, and that's in kilogram per cubic meter. So at the end, that gives you kilogram per day, and we want to change it to kilogram per second. Okay, because joule, if you remember, joule is watts per second, right? Because the units of delta H.
Watt is joules per second.
Huh?
Watt is joules per second.
And watts is joules per second. So we have, this is kilojoule. Let's make bit if the units make sense. Okay, power equal to delta H polytropic times the mass rate. This is in kilogram per second, and this is in
Kilojoules per
kilojoule per kilogram. And then these two cancel each other,
It's kilowatt.
and
Kilojoules per second.
yeah, kilojoules per second, which is kilowatts, right? So it makes sense. Okay, and then we divide by 1,000 to get in megawatts. Okay, and let's see if we get a nice number. Otherwise, we did some mistake. Oh, let's change first to seconds, and to change to seconds is 1 day is 24 hours. 1 hour is 3,600 seconds. Okay, so we have to divide by 24 and 3. So actually, this number is going to be a bit smaller than what we. Okay, and then so that's mass in the right units, and here I have power. Here I have in megawatts, and I'm going to just to multiply these two and divide by 1,000, right?
Yes.
65 megawatts.
No, there's something wrong with the units of.
Okay, so I think we made a mistake here. It should be 8.3. Yeah, no, that's too small.
It's fine because we have RP of 1.03. It's totally fine.
Oh, yeah, might be because it's too small.
Yeah, because we don't have a compression ratio 1.03.
Yeah, let's on the break. I will check the values, but I think this should be with 8 point. Okay, I think to make for the because of the units. Okay, now what else do we need? We need now, if we want to plot it, we don't need that exactly for now, but for later, if we want to plot it in the chart, we want to do this conversion, right? From the actual conditions to the conditions of the test. Okay, and for that there are two equations that are also here. Transformation of operating point, okay, to Q test for Q, and there should be one for H, which is not here. I don't know why. So I'm going to pull it from the solution. See, it's a bit slightly more complex than than the pump. Okay, HP in the test. Okay, and then you have Q actual at the test conditions, and this Q actual is in cubic meter per day, and this HP is it per day, or how is it in the plot? Yeah, per day. And this HP is in meters. Okay. So what do we need for that? I think the name of the expression is Q test equivalent and HP test equivalent. So let's do that. HP test equivalent, and here we need the HP of the actual, which is this one, but divided by G. Remember? Oh, that's something that was missing also here, right? So here we have to multiply. Multiply. But why is it so small now? Before it was 400, right? Or not? Ah, but I put here a point. That's correct. Yeah. You are awake. That's good. So HP test equivalent, and here we need the HP, but divided by 9.81. The temperature at the suction, that is on the left, and that should be also in absolute. Then the T of the test, I put it here someplace, here. Okay, that should be blocked. Then the K of that I have is this one. That should be also blocked. The K of the test, that is here, and that should be also blocked. And what else? The molecular weight of the test is, that's air, but I need the molecular weight. What's the molecular weight of the air? 28.97. And the molecular weight of the fluid that I have is yeah, the rest is going to be easier. And this one is 16. HP. Okay, so I give a very small number, and then the actual, again Q actual test, and I have the actual rate, which is here. Then I have the temperature, which is here. Then I have the temperature of the test, which is here. That has to be blocked. Then the K that I have is this one. That one has to be blocked. The K of the test here, that one has to be blocked. And M 28.97 and molecular weight 16. Okay. Now let's take a break, breathe, and now we go and apply that. That was for the first year, but now we have everything ready, and we just have to pull down to see what happens in the other years, how it's going to behave, the compressor. Okay? So let's take a break, 15 minutes. To all back scenes that you are not supposed to see. In class everything should go perfect and smooth. Sometimes it doesn't go, but so I recommend just look at the expression for the polytropic head, okay, for the polytropic enthalpy, and see what are the units of that, okay. So so let's say here we have a small section, we see cheese debugging. Okay. And we want this unit to be, we don't know what is this unit, okay? But we know temperature is in Kelvin. Set doesn't have any units. These are, what are the units of that? This could be kilojoule per kilogram Kelvin, right? This is the no mole because this is not the universal. When you divide by the molecular weight, you get rid of the mole. Then N, and all of this doesn't have any units, right? So at the end, this is what we want, kilojoule per kilogram, right? But it depends how we introduce the R. If R is in the universal constant, if it's 8314, that's in joule kilogram mole Kelvin, right? But if it's 8.314, that's kilojoule kilogram mole Kelvin. Okay, so it depends how we are using this this R. Okay, so let's see. Let's go back. So we are using it like joule. So this, instead of being kilojoule, should be joule per kilogram, right? Because we are using it 8314. Okay. And then here on the power, we have to divide by, instead of 1000, by 1 to the power of 6. And here I have to return and stop cheating and just go to what we had, that was 21. Okay, because I changed to 22 to see. Okay. So we hope it's okay. We trust someone else there taking care of us.
Can we check also
The
the discharge temperature?
discharge temperature. The discharge temperature is 85, and what I was getting in my 99, but this is for different properties, so it should be okay.
No.
No?
Can you go to the expression?
To the expression that I was using. This is R P to n minus 1 over n times the temperature at the inlet, which is 67, but it has to be in absolute, so plus 273.15.
Yeah. Why do we minus again by that one?
This one, because the temperature that we are going to get is in Kelvin, and we want to subtract by, okay,
So you are returning back
to Celsius. Yeah. Okay. Any? Well, I hope now it's okay. So let's see. All of that is calculated. Let's see if I put the recording. Okay. Now what I have to do is just to drag. Okay. I have to drag to some other, to 21, to see what happens with time. Right?
You chose 22 after 20.8.
Oh, should be 21. This is 22. Okay, because I'm doing it immediately after. Maybe for the first time after I install the compressor, I won't need the compressor because there is really not much pressure boost. Like you saw, it's something very small. But then with time, then I have to start, using it to. So let's drag. Let's see if it works. Let's drag all of that and pull it down. How many do we have down? 1. Oh, again it's wrong. Okay, so let's drag it just down here. Something happened. Okay, so let's see what happens if it makes sense. Just the second year. Okay. Hmm? Okay, should be 30. And the rate, why is the rate changing? Yeah, it's 20. What else? Here I have a problem. Value. Okay. Yeah. Here we will see that later. Just let's focus on the year, on the second year, 22 after compression. Okay. So we have the temperature at the suction should not change. Should be also 67. The NP should be, again, we are saying that doesn't change. What else? Nothing else, right? So here on the second year, everything seems to be working okay according to our requirements. Okay, the temperature at the discharge has to be less than 150, which is okay. Then the compression power, I have something very small, okay, 0.00 megawatts, That means that actually the compressor doesn't have to work.
643 kilowatts.
Okay, here there is something wrong. 85. Maybe one of the properties is not. I think there is something that is not frozen. It's
It's in HP
Huh?
test.
What?
In HP test, the second line, you haven't blocked that specific gravity there. B14.
Yeah, but I think what is bothering me is this 654. This value delta HP seems to be too high, and I don't know why. Do you see any mistake? Maybe here. Oh, we didn't froze this one. You see, so it's going down. Okay, so let's freeze that. So this is just to show you how you shouldn't do it. So you learn and you do it the proper way when you deliver the exercise. Okay, mass flow is constant, which makes sense. And the power is still high. Why?
120 megawatts.
Maybe this one also looks a bit high. So why is this too high? Is
8314 R.
Oh, here. This should be also frozen, right? You see, that's the problem when you don't lock the cells. And let's see, that's the only one that we have. Yeah? Now we are getting exactly what we were getting before, 4.2, right? Megawatts. Okay, so let's see. The delta P and the RP. Okay, what do we, let's maybe copy that, okay, and let's put it in to analyze it one by one. That's phlegm, that's the discharge, and we need the pressure at the suction also. Okay, so let's copy this because it's a bit messy to do it here in Excel. Okay, we have some issues here, but let's just look at what we have so far. And we have to put on top of that, we need the suction pressure. That is actually this one here, okay? This is the suction pressure, right? Suction pressure, it's this one. And do we need something else? Not for now, right? I think. Yeah? Okay, so let's see, let's look where do we have problems. Where do we violate? This is pressure at the suction, and this is in bar. Okay? We said that the pressure has to be greater than 20 bar. Okay? So where do we have violation? In this year. Okay, year, this was 21, 22, 23, 24, 25, 26. So in year 6 of compression, we are going to have a problem that the pressure at the suction is less than 20. Okay, this is year. Okay, so we have to take some actions here. Now let's go to the temperature at the discharge. No, let's see what else. T suction, we have no issue here. Delta P, we have no issue here, no issue here. The next one is temperature at the discharge. The temperature at the discharge has to be less or equal to 150 degrees. Okay? And we see that everything looks okay from this point. Here we begin to have problems. Okay, and that's exactly the same year, right? Year 25. Okay? So it looks like in year 25 we're going to have to make a change. Okay, we have to so far, but let's continue. We have Q local, we have this, here we have no constraints here in power. Okay, what are the constraints in power?
22 megawatts.
Okay, 22 because we have two compressors. Yeah, right? Is it the same to have, because what we are doing here is assuming that we have one big compressor and we are calculating delta H times, is it the same this than doing this? Yeah? Is the same? Yeah? Because the delta H will be the same, okay? Because you're going to and from the same pressure and temperature. You're going from the same P inlet, T inlet, to the same P outlet and T outlet. But the thing is that you can compute it like this, total times delta H P, or you can say M total divided by 2 times delta H P plus M total divided by 2 delta H P. Okay? You can do it both ways and they're going to give you the same. So this power that is reported here is actually the power of compressor 1 plus the power of the compressor 2. Right? Yeah? And if you see this, the maximum that we have is 22 megawatts. That means 11 per compressor. So we're going to have problems exactly here, which is where? The terrific year, okay? It's the year when everything is going to crash, okay? Everything is going to explode. So we have to take actions there. Yeah. So what can we do?
First install cooler upstream of compressor.
Cooler can attack this part, okay? Cooler, that helps with that part. But it's probably, I'm not sure if it's going to help here. Okay, the power. Maybe it will reduce the power, but I'm not sure if it will reduce it to 22. We can try. But what do you recommend here to do what could we use? Solver, please. Okay. Okay, so let's say now that we have here, we need cooling, okay, from this here. So we could be bypassing the cooler, but in this time we have to use cooling, okay? And the cooler, I told you, that creates a delta T of 27. So at the end, this temperature will be 50 in this here, exactly. And then probably I will need the cooler after that.
40.
Huh? 40, okay, 40. Yep, and let's see if the temperature change. The temperature here is now okay, it's within the range, but now this temperature is still out. Let's see the power. Okay, 25, still too high. So let's try with the solver, okay? Let's see, our dear friend solver, please. What do we want to do with the solver? What do we want to change?
Power.
It was year 25, right? Yeah? Is this year or the previous? I think it's where we have the violation is here, and that's which year? 25. Okay. I say, please solver change. I want to change the rate of the field, okay? How much I am producing. That is this 20 here value. And I want to, so what do I want to maximize, minimize, or?
I guess you have to change the power by.
Okay, let's put first the constraints, okay? So let's say the power has to be, this power has to be less or equal than 22, okay? Then I want that the temperature has to be less equal than 150, okay? Then I want that the suction at this, the pressure at the suction, which is this one here, has to be greater and equal than 20. Anything else? No? Okay, but how do I run it? I still have to make here something. Could I use the same variable? Okay, I want to produce as much as possible, really, but I want to still to fulfill all the operational constraints, but I want to all the time to produce as much as possible, okay, by changing the same rate. I think we have done this trick before also with the pump, right? No? Well, let's see if it works. Okay, found the solution.
Is set 0.
0. Oh, sorry, yeah. Maximum, okay, not 0. Okay, why did it increase? Oh, and has to be less than 20, okay? We don't want to produce more than the plateau. So this value should be less equal than 20, e to the 6. Yeah, and that's all. And for now I have to change back to what we had. Okay, now it told me that I have to reduce to 19.6. Let's see if all the conditions are met. The temperature is 134, which is quite okay. The power is exactly 22. So you know where you're going to be operating there, on the outer, on the highest RPM. Okay, you're going to be operating on that line. And yeah, nothing else. Okay, let's try to do the same thing for the next year, which is a bit more challenging, 26. So here I'm going to change everything, 1 down, 50, 50, and here we also have 50, and here we also have 50, and 50. Right? Solve again. Now it went down to 18. And now let's see, before the limiting issue was the power, and now we have the temperature. Is it still okay? Then the power is exactly 22. So again, the limiting value is the power. Okay. So here we know we don't have to try with 20, but we have to try with a smaller number. Okay, so let's try, for example, 16 e to the 6. And let's try maybe here also 16. Okay. So and again, let's solve once more. 51, 51, 51. Ready? Okay, and now it went down to 16. Okay, now let's see if everything, the temperature. Okay, so now you see the temperature is on the bound. That means that at that time becomes the limiting factor. So maybe I won't have, let's see the power. What else did we have? Oh, the suction pressure also. Let's see, the pressure at the suction is 26. So it's still okay. Let's see here.
Powers makes 21.6.
Here, what did I get power? Yep. This one, right?
No.
Oh, this one. See, we still have some mistakes every now and then that are chasing you. chasing us. Okay. And here, did I make the same mistake or not? Yeah, here is blocked. Okay. Okay, so now actually it's not limiting on the power, but it's limiting on the temperature. And let's do one more because I don't want to continue on this very fun way of doing things. For that it's better to use a macro, but now you see the power. If you have to do that run, I don't know, so many years, and if the boss asks you to do it every month, then you're going to cry. You're going to be there the rest of your life. So just please use macro, take that into account in your professional life. Okay, now it went to 14, and let's see, the pressure at the suction is still okay, 24. The temperature is still at, so actually I have to reduce the rate because otherwise the temperature will be too high. Okay. And yeah, the power is no longer a limitation, so actually I use 22 only for 2 years, the maximum capacity of the motor. And then after that I began to go back and reduction. That's impressive, right? So actually you don't use the full potential of your compressor all the time. You use it only for a few times. And then you have all the other constraints is what define the way your compressor is going to operate. Okay? Let's take a screenshot of that. Just first a screenshot of the solver. Okay? This is it's a trick. It's like saying, it's a bit stupid to say I'm going to change the variable to maximize the same variable. Okay? It doesn't make sense. But what makes sense is that you put all of these constraints, and then it cannot just increase whatever it wants. It will try to be all the time producing at the highest, but fulfilling all the other constraints, all the other operational constraints. So let's copy that. I'm going to publish this file on its learning. And yeah, so let's see. Okay, so here is field rate. Okay, and the field rate is actually in both. You have to use maximization because I want to produce all the time as much as possible. And then this is the total power. Has to be less equal than 22 megawatts. I have that motor, I cannot give any more. Then the field rate has to be less or equal than 20 million. That's especially when I could produce more, but I don't want. Standard cubic meter per day. Then the next thing is that the pressure at the suction has to be greater or equal to 20 bar. And in our case, that doesn't happen, so we are okay. And the temperature at the discharge has to be greater or equal to 150 degrees C for multiple reasons. So now let's see how the results look like, what we obtained. I don't know what's happening here. But this one we can plot the pressure at the inlet and the pressure ratio. Okay, so let's see, this is the pressure at the inlet. And where is that? Okay, so for all years it's up to year 52. And here this is not this one, but it's actually this one, right? This is the pressure at the suction, yeah. P-plane available. And 44. Should be 44 or 45? 44. Okay, so actually the trend looks okay. The pressure at the suction goes down with time. Okay, and now let's see RP 4452, and RP should be on this column. And I think this one is plotted on secondary axis. Okay, so this is the pressure ratio, and this is the pressure at the inlet of the compressor. Okay. Okay, let's copy that, and I don't know why this is up to 9. Okay. Come on. Yeah, you see it's a bug. You cannot move it from here. Okay, so I copy that. Okay, so suction pressure goes down with time. That's suction pressure. P suction. And pressure ratio goes up with time. Okay, but not much. Still is within the limits that when we saw initially, when we run without the solver, we saw actually that we saw a very high number, 20. Okay, usually the compressor should be all the time between 1.0 something to all the way to maybe 3. 3 is already too high, but that's typically compression ratio of a compressor. Let's see how the rate goes in time. I think that we have to create one new plot, right? Okay, so we delete this one, for example, and then we put here field rate. Time, and here we select and edit, and it's on column actually C. Okay, 44 C and C. Okay. And we can put it also with points because it's interesting to see why do we have to reduce the rate. Yes, and I'm about to, we're about to close the session, so just be patient. A bit more. Why that came up? Okay, so in this time I had to reduce the rate because of the
distortion pressure and power.
And power. Okay, power here is equal to 22 megawatts. Here I had to do cooling also first. Okay, here I had to do cooling. Okay, activate cooling. Okay. Then at this point I was also operating at 22 megawatts, but nothing else. And then in this point I had to reduce the rate for the temperature to be exactly equal to 150 degrees C, the temperature at the discharge. Okay, and from now that point also that becomes delimited. The power is less than 22 megawatts, but the temperature of the discharge is already locked in 150. So that's why it's so important also to foresee if I can make a better cooler, if the cooler can operate more efficiently to take it down closer to 6, okay? Because then I will be able to produce more. Instead of having to reduce the rate, I could produce more because I still have compression power to use, okay? Yeah, so I thought about before on these minutes that we have, if we try to plot on this pressure map that we have, if we try to plot the points that we have already made the effort, so it should be quick, I think. Okay. Okay, those are the points, so we have to take them away. Okay, so we are going to plot okay, on the plot of the test data. So we have already converted the actual values, the polytropic head and also the actual rate, to this test using these correction coefficients. Okay, that we didn't go too much in detail, but that's the way it's done. And we want to plot it on the compressor map on the test conditions to see how they look like. But remember here, this compressor map is for one compressor. So we have to, the rate, the height, the head is the same because they go from the same pressure to the same pressure, but the rate has to be split into two. Okay, so we have to put here one more column that says, or we can just say Q act test of one compressor. Okay, single compressor. And it's going to have exactly the same units. And we say by 2. And then we are going to plot this versus this on the plot to see how they look like. Okay, so let's go to the plot. Not this one, but the operating points. X is this, and H is here. Okay, I'm not sure if we can put, I think if they are increasing and then you have a, can you put them with tags with each year? I think we can do it. I think if you select here if I select I think you can put the how do you put the layer?
Show label.
Huh? Show label, but then it's going to show for all the other points.
But you can just select the points you need.
Yeah, can I do it here, for example? No.
No.
Because how do you know which year? I think this is the first year and then you're going on this direction, but when do you know when you're going back? Huh? That's a question for Bill Gates. Huh? No?
Each point like a separate series. Like a point.
Yeah.
Yeah, that would be an option. So you want to do it like that before we go? Well, let's do it very quickly. But we don't want to go too late. So this is for year. It's going to take a bit 21. Okay, so we can just write it here 21, and that will be 45. Okay, then one more, 22. We go to our, we take this, and we take this. Then we go one more, 23. This class is the perfect example how not to do things. 3, then add one more, 24, and we were here. Okay, now change it, put it very ugly. 24, 25. You know, please someone find a way to do it so we don't have to be here doing this. $27. Let's see here.
So it was 26.
26, okay. That's 27, and here, and then we have 29, 28. That's the last one, hopefully. Okay, so 27, 28, 26. So here there is something that doesn't make sense. Okay, we'll just have the discussion on that. So what happens with these points? Will I be able to operate here? No, because it's outside of the compressor map. So what do I have to do? I have to increase somehow the polytropic head. Okay, I have to increase the rate. So in those cases, what can be used is after the cooler, here I put a valve. Okay, that is going to be active only during the early years of the operation of the compressor, and it's going to create an additional pressure drop to increase RP, or to increase delta P of the compressor. Okay, so these points will go up. Okay, and that's part of the things that you will have to do in your exercise, to check when do you need to add this valve for the points to be up. Then you see that it's going to progress up and up and up. But one thing that doesn't make sense is that when do we reach maximum power? I think it's year 25, right? I think.
20.
Maximum power is here, and which year is that?
25,
25. Okay, so one thing that doesn't make sense is this point, that all the other points should have the same power. Okay, this point 26 should have the same power.
I guess it's against polytropic head, and we have reduced the flow rate, because to calculate the power we have to multiply mass flow rate with h.
Well, it's not so clear from that's going to be the question for the exercise. Why the points go on, they don't stay in the same place. You have to think about it. Okay? So the main verification that you have to make is that the points fall on the diagram, okay, inside the diagram, and in this case we see, okay, it works quite okay, for all the points. The only issue is these points, the first 3 years, and we see that the conclusion is that we have to put an inlet valve, okay. Here we have the scrubber, and here we have our compressor, okay. Additional valve is almost like a choke, okay, or it's a choke that we want to reduce the pressure at the inlet, so the compressor has to give more delta P. And really that's a thing that's not very intelligent to do, because we are removing pressure to add pressure, but it's only to allow the compressor to operate properly, okay, to put the points inside the operational map. Okay? But the rest looks okay. Now the trend, I don't know if that's correct or not, maybe we have made a mistake, but yeah, we have to find what's the reason. Okay? Any questions? No? Everything is clear? Crystal clear? Yeah? It's a long exercise and you have to calculate a lot of variables. But just because you're monitoring also a lot of variables, okay? You need a lot of temperature, you need rates, you need everything and in different points of the system. But you have to be sure, or you have to be clear how to calculate and what's the justification to calculate everything in the system, okay? Which equations do you use, why do we use them? And the last point, so first we have done a simplified analysis, which is we don't have too much data, we just use the main constraints, and then we had the compression map, and actually we have to verify that the points fall inside the map. And you see we did quite okay. The only thing was at the beginning we have to do something else. Okay. Well, thank you very much. See you next Monday.